This is the first webinar of a series of 4 and up to 9 Q&A sessions that the IEA Energy Storage Task 45 group is going to organize. And the first webinar of today is about the planning, regulatory, societal, and financial dimensions of large-scale thermal energy storage implementation. So I'm quickly gonna go through the workshop program and also introducing the different presenters. So we're gonna start with an introduction and brief technical overview of large thermal energy storage, especially based on the deliverables that were made for IEA Energy Storage Task 39. Then we'll go through 3 different examples of planning, integration, and regulatory framework on 3 different technologies. So Aquifer thermal energy storage by Bas Gottschalk from DTES BV. Then on the Borehole thermal energy storage by Lukas Seib from the Technische Universität Darmstadt. And after a break on pit thermal energy storage by Per-Alex Sørensen from Planergy. After that, we're gonna go through the European framework for large thermal energy storage by Johanna Schickling from Hamburg Institute, and then the stakeholder engagement and public perception in large thermal energy storage by Michelle Claudia Phoenix PNT. And finally, Geoffroy Gauthier from Planergy will present some large thermal energy storage financing methods, and we'll end with an open discussion if time permits and a wrap-up of the workshop. Yep. If you have any question during the workshop, please fill up this form. I'm also going to put the link on the chat. There you go. So basically, questions will be considered at the end of each webinar, if the time permits, or during the planned Q&A session. And I will present the schedule of this webinar and session at the end of the workshop. So I'm going to start with presenting and introducing the IEA Energy Storage Task 45 project, which is a 4-year project whose goal is to accelerate the uptake of large thermal energy storages. So it is a project that is gathering 22 partners from 7 different countries. It's a follow-up of IEA Task Energy Storage Task 39, and the title was Large Thermal Energy Storage for District Heating, which ended at the end of 2023. And basically, as I said, my presentation is going to go through some of the deliverables that you can download using the QR codes over there, and I'm also going to put the link of the website. The QR code doesn't work, or it's easier for you to use the website. The task is divided into 4 different subtasks. So the first subtask, numerical simulation, goal is to further improve the numerical simulation to have better tools for system design, integration, and optimization. Task B's goal is to broaden up the LTES material database and material test methods. Subtask number C aim is to set a basis for future standards and performance checks for LTES systems. And finally, subtask 4D is to disseminate targeted information training material for decision makers, implementers, and developers, as well as to make an inventory of improved concepts and technologies. And this, I'm also going to mention this inventory of improved concepts later at the end of the workshop. And as you can imagine, this webinar is basically part of this subtask D. So the task scope basically cover the four main LTES technologies and improved concept. So the four main technologies are the one represented on the sketch here. So tank thermal energy storage that can be either above ground, which is the most common case, but also underground or semi-underground. There's also the pit thermal energy storage, the borehole, and the aquifer. But I'm basically gonna go through the different. I'm gonna present the four different technologies in the slide right after. But basically, storage technologies would have to meet some requirements. The first one is that the yearly stored energy has to be greater than 1 gigawatt hour. And this basically kind of represents or would be enough heat to supply the demand of 62 households over a year, just to give you an order of magnitude. Then the typical storage temperatures for district heating are usually 100 degrees, but technologies can also go up to, for example, 120 degrees Celsius for improved concept. The task also kind of work on technologies with a high technology readiness level, so quite mature technologies. And storage system that can be used for either daily, weekly, or seasonal storage for district heating, but also industries. And the storage medium can be water, soil, or other things. So as I said, I'm going to start. I'm going to present the four different main technologies, starting with the tank thermal energy storage, which is essentially cylinder of steel filled up with water, treated water, and which is insulated from the top and the sides. And you can see a sketch here where basically there are two, or at least two, but also sometimes more diffusers to basically be able to charge and discharge the storage system. And the heat is stratified, so you would discharge. I mean, in this case, it's like a sketch of charging process where you would take out extract water from the bottom and put hot water on the top. Some overall general technical characteristics. So usually the volume can be between 1,000 and 56, or that's at least the maximum so far, cubic meters of water. And the max thermal power can range from 1 to 1,000 megawatts thermal. And this basically depends on the size of the pipes and the diffusers, but the range is quite wide. It's usually used for daily or weekly storage, considering the relatively small size of the storage. And it's a very mature technology, and with many implemented projects listed. One example was chosen by the task 39, which is a TTES in Berlin, in Germany, by Vattenfall, that was commissioned in 2023 with a water volume of 56,000 cubic meter and a storage capacity of 2,700 megawatt hour, and very highly utilized because the storage charge and discharge cycle was quite high, 70 to 120 cycles per year. The second technology is the pit thermal energy storage, which is essentially a pit that is dug in the ground and which is insulated, always at the top, sometimes also at the sides. And basically, the idea is like to dig soil and to put it on the side, so as you can kind of minimize the cost of the storage. Yes, and otherwise the way you can operate will be the same as a TTES with diffusers. The size of the PTES are usually can be quite high, quite big, from 20,000 to 1 million cubic meter of water, and with the same kind of thermal power output input. And that can be also used for seasonal storage because, I mean, that was how it was at first implemented, basically storing solar heat from summer to winter. Also quite mature technology, but a bit less implemented project 7, but a bit more in 2025 and more are to come. And the example that was chosen was the one in Groningen in Denmark, with a water volume of 60,000 cubic meter and 2.5 cycles of charge discharge per year. And we can see here the solar panel field, and here the pit thermal energy storage. The third technology is the borehole thermal energy storage. So basically, it's a storage where the heat is stored directly in the ground, and the storage medium is soil or rock. And basically, it's a series of boreholes where heat exchangers are inserted in order to transfer heat to the surrounding soil. So we can see here a sketch of a charging process and discharging process. And basically, the PTES slit is usually covered with soil after implementation, which means that the surface can be thereafter used for other purposes. The size range is a bit similar as pit thermal energy storage, from 20,000 to 1 million cubic meter equivalent volume. And however, the thermal power is usually lower for boreholes, only from 2 to 50 megawatt thermal power, and usually used for seasonal storage. And the example chosen was the one in Emmaboda in Sweden, commissioned in 2010. So 140 boreholes, and the storage capacity of almost 4,000 megawatt hour with a totality of 20 degrees. And the last one is the aquifer thermal energy storage, which is basically using the aquifers, the groundwater and the soil and ground underground to store heat. And usually there are two wheels, one cold and one warm, where you can play around depending on the season to either extract or put heat or cold in the soil, in the aquifer. This can be quite large system, usually used for seasonal storage, and fairly low thermal power. And the example chosen was the one in Middenmeer in the Netherlands, commissioned in 2022, and with a storage capacity of 28 gigawatt hour. And you can see here the two wells, the cold and the warm well, separated by a bit more than 200 meters. And quickly, so with the last slide, so basically the large thermal energy storage usually benefit from big economies of scale, with lower cost per unit and better thermal efficiency. We can see here for example, for the TTES with the blue triangles, the PTES in orange, and the PTES in green. This kind of economy of scale of specific investment cost. And here's the storage volume. And my last slide for today would be that the key message was also from test 99 that the LTES can be used to cover a wide range of application. With, for example, so this is the LTES total storage volume, and here's the maximum heating power. With the TTES, that provide a wide range of heating power, but it's kind of limited in storage volume. And compared to that, the PTES can go in much higher, greater volume, and also high power, maximum heating power. And the PTES and ATES can be very large system, but with a usually fairly, lower heating power. And the IEA Task 39 group, let's say, classified the whole project, and divided into 4 different parts, 4 different phases: opportunity, design, tender, and implementation, and classified the different stakeholders that would be involved throughout the whole process. But my colleague Geoffroy is gonna mention this slide and explain a bit more at the end of the webinar. So thanks a lot for listening to this introduction. And I'm quickly gonna go give the floor to Bast to talk more about the planning, integration, and regulatory framework on an aquifer thermal energy storage case study.
Okay, thank you very much, Romain, for your nice introduction to the different technologies. Share screen.
Yeah, we can see your screen.
Yeah, we present.
Perfect. Yeah.
Perfect. No,
and Bas, take your time for your presentation. We have a bit of buffer, so take the 20 minutes that you need, and yeah.
Okay, I'll
Go ahead.
30 minutes. Thank you. Let me first introduce myself briefly. My name is Bas Gottschalk. I'm the owner of the TTES company, and TTES stands for the Dutch Thermal Energy Storage Solutions. And our focus as company is to promote and to develop the shallow and deep geothermal energy projects with a focus on the ATES, high temperature ATES. So I'm very happy that I can present more about these technologies in this presentation. I'm a Dutch-based company, but I'm active in all kind of countries in Europe, but also in the US, in Japan, Korea, because what we see is that the technology has been well developed in the Netherlands, but we see that the demand to the ATES technology is huge in other parts of the world. So we are happy to share our knowledge and experience and help other clients to implement this technology. Now, as mentioned already by Romain, he had given a very nice introduction about our task 45 and 4 major technologies where we are looking for. It's mostly on the large scale heat storage, and our purpose is to accelerate the uptake of large scale test systems. And the focus of my presentation will be to focus on the Aquifer thermal energy storage systems, which is in the right bottom side. Now, maybe it's good that we start with the traditional ATES concept, and then we look further to the middle range and the high temperature ATES systems. But the basic understanding of the ATES system is that you have 2 wells where you can abstract and inject groundwater from aquifers. An aquifer can be a sand aquifer, can be a limestone or sandstone. But most of the systems in the Netherlands are using sand aquifers for the abstraction and injection. And the ATES system is in fact a kind of battery, and the traditional system is a battery of heat and cold. So what we are doing is in the winter season, when we need more heat, then we abstract warm water from the warm well. We use a heat exchanger to exchange the heat. use it for the heating, and then the cold of the building will be captured and will be stored in the cold well. And during summertime, we have the opposite pumping direction. So then we abstract cold water, we cool down the building, and then we take out the heat and store it in the warm well. The typical temperature range for cold is between 5 to 10 degrees, and typical abstraction temperatures from the warm well are between 13 to 17 degrees. So you can imagine that in the cooling mode, you can use the low temperatures for direct cooling of your building. In the heating mode, you still need the heat pump to increase the temperature level to 45, 50 degrees so that you can heat up your building. Typical flow rates are between 25 to 250 cubes per hour, and wells are often installed at a depth of between 40 to 250 meter below surface level, depending on where are the aquifers or where is the best aquifer. When we think again about the heating and cooling possibilities, that what you see is that in the cooling mode, we only need a little bit electricity for the abstraction of cold water, and then we have a direct cooling of the building, which will produce a very high coefficient of performance, COP, between 30 to 40. So it means that one piece of electricity generates about 30 to 40 parts of cold. Now, when you compare it with traditional air conditioning has a COP of 3. So you see that using the ATES is about 10 times more efficient compared to traditional air conditioning systems. When you look in the heating mode, you see that the COP is between 4 to 5, which means one piece of electricity generates 4 to 5 parts of heat. And that's the reason is simple, because we need a heat pump to increase the temperature level to the 40, 50 degrees, and that has often a COP value of 4 to 5. So one of the ideas is, can we also improve the COP in the heating mode? And one of the clients, an ecology institute in the Netherlands, in Wageningen, NIO, they ask us, can you also think about an ATES concept where we can remove the heat pump from the system to increase the efficiency? And that's where the idea was created of the middle range ATES system, middle range temperature ATES systems, that we store higher temperatures from solar collectors and waste heat in the subsurface. And then we could abstract it with a temperature of about 50 degrees and use it for direct heating of the building. Now, in that way, we have a much more higher COP because we don't need a heat pump for the heating mode. Now here you see the opposite of the same building, which is already constructed more than 10 years ago. So there is experience with how to use the middle range ATES system. There's a lot of monitoring done also to the chemical and change in microbes, which generates a lot of information also for further and future development of the technology. A very other interesting project which is under construction right now, it's the Butterfly Orchids greenhouse project, where we will collaborate with the Uses for Heat consortium, which is now changing their program to make it possible that this new project will be integrated, where we will abstract and inject temperatures up to 50, 55 degrees for also large-scale heat storage for direct heating of this greenhouse. But can we also go up with the temperatures? Because Romain also mentioned that in district heating systems, you need much more higher temperatures. Now, in the example we have is the Middenmeer project, where we went up to 80, 85, 90 degrees, which is the high temperature ATES system. The definition we use is chosen by us. I will explain why. in the next slides, but it's not an official scheme, but we often use it that for traditional ATES system, we have storage temperatures between 5 and 25 degrees, middle range temperature between 30, 50, 55, 60, and high temperatures up to 90 to nearly 95 degrees. Now, why should we use high temperature ATES? Because we have a surplus in summertime of heat, which can be produced like by geothermal systems, high temperature geothermal systems, and we often have a demand of heat during winter time. So then the idea was to buffer the surplus of heat in an ATES system and then reuse it in the next season. So at the moment there are all kinds of concepts where the high temperature ATES system will buffer heat from sources like geothermal wells. Very popular at the moment is also the solar collectors, but you can also combine it with waste heat, industrial heat. There's also now a connection with the electricity network that you can convert surplus of electricity into heat, or another way is that you also produce electricity by using CHP, and then that the surplus of heat, which will also produced in the same time, and will be stored also in the high temperature ATES system. So in fact, it doesn't matter so much what is the heating source, but you need to take it into account when you design it. On the user side, we have all kinds of other uses like district heating systems, greenhouses, residential areas, etc. Now, the example which was mentioned already is a full-scale project in Middenmeer, where we installed the ATES system at nearly 400 meters depth. And the storage temperature is about 85 degrees with a maximum flow rate of 150 cubes per hour. Now, when you compare the technologies, the traditional ATES, middle range and high temperature ATES, you can see in the first line that the storage temperatures will change, but the idea is that for the ATES and the middle range temperature ATES systems, we use traditional materials like the PVC screens, which are cheaper, more easy to handle. So that makes it also more cheaper in total. But for the high temperature ATES systems, we need composite materials. Water treatment for the ATES systems middle range, it's not really necessary. For high temperature, yes. Effects on the groundwater, we did a lot of work to monitor it, but we don't see really big impact on it. Now you can see at the energy displacement that the higher the temperature, because you have a higher delta T, you can also generate much more heat in each season. Now the first technologies are quite proven, common technologies, and you see on the high temperature ATES more development is still needed because you have the higher temperatures. So what kind of materials, components do you need, and what's also the impact on the environment? Now, I didn't include a cost indication, but very roughly speaking, you can say that ATES system will have a cost price level of about €500,000, €1 million per system. Middle range ATES more or less the same, maybe a little bit higher. And for the high temperature, you have to think about 5 million and more. Now, how does planning looks like? Of course, you start with feasibility. We highly recommend to do test drilling, the permitting process, design, realization, construction phase, and also the exportation. And at the bottom, you see a very indicative timeline, which is also depending on the client itself, its decision moments. No. some of the processes can be done in parallel, but at least what is our experience that such a development will take about 3 to 4 years from first idea to the exploitation phase. Now I will dive in a few more aspects of the process. The first is the very important step 1, the subsurface investigation, normally done by desktop study to first look in the central database of all hydrogeological data which is available to make a first inventory of the subsurface conditions. And second, we recommend to do test drilling to to make your interpretation and data much more accurate. Very important aspect is that we look at the clay cap, which is above the aquifer. Of course, we need to have the aquifer properties itself and also the layer below the aquifer, because they have an impact on the capex and they have an impact on the opex. Because you want to know the properties, because the well capacity also determines in combination with the heating demand, the amount of wells, so also the investment cost. So critical parameters are the thickness and the permeability, and the storage efficiency will also be influenced by the thickness and the properties of the clay layers. So that's something we take into account in the initial phase. Now, the second phase is also to look how can we integrate the high temperature ATES system in district heating network, or how to combine it between or buffer between the heat source and the heat user. What is exactly the function of the ATES system? Should be a short-term buffering or should it be seasonal, of both? How do you want to use the system in that way? What are the operational conditions? What are the injection temperatures, abstraction temperatures? What is the storage temperature? How big will be the volume? Till which temperature do you abstract the groundwater? What is your cutoff temperature? Now, such a kind of operational conditions are very important in the design and the system integration of your system, because it all determines has an impact on your business case, and that's what you finally want to calculate and see if it works. Now, the other things is very important are the legal aspects. For the traditional ATES systems, the framework is that you can abstract and inject between 5 and 25 degrees, and that you should have an energy balance. So that means that the amount of energy you abstract and inject should be more or less equal. When you want to apply for a permit, you have to take into consideration other groundwater users, so you're not allowed to harm other interests. So that's something you need to prove by setting up a risk assessment. For the high temperature or the middle range ATES systems, the injection temperature will be much more higher than 25 degrees. And of course, because you are making a heat buffer, you don't have an energy balance. So that's something which deviates from the actual legal framework. And therefore, a new conceptual framework has been prepared, which is now used by various authorities. But it's still in progress and will be tested and developed. Which means that we have to do sometimes some extra efforts in the procedure, do some extra monitoring, and also having more frequently evaluations. Now, the effects, I don't want to go in detail too much because my time is running. What we have done is a lot of research to what is described in literature and what we have measured in the actual ATES systems, and also the middle range and high temperature ATES systems. Important aspects are to look at the calcite concentrations, the dissolved organic carbon, silicium, arsenic, and also ATP is a standard to measure the microbiology trend. Our very general conclusion is that the changes are often quite acceptable or minimal. You have, especially for the high temperature ATES, you have to do some extra efforts, especially to present calcite precipitations. And the other recommendation is often just to monitor what is the chemical composition of the groundwater and also the microbes, but more to see if there's any change, not because we expect serious risk. Now, a few pictures of the construction. From the left side, you see the drilling rig, you see the installation of the monitoring screens, the blue pipes, the wellhead and the pipings. And on the other side, you see the final construction. This is for the high temperature ATES, which is more complex than the traditional ATES systems. And on the right side, you see the heat exchangers in the technical room. Now, the last slide is the monitoring, which is of course very important. What we now do is we make a good profiles and measure the temperature development. We measure the micro and micro elements in the groundwater, and also the ATP to see how the microbiology is developing. And you can have more improved glass fiber optic measurements of the temperature, which you can see in the blue screenshots, which gives you a very nice idea how the temperature will develop during time. Now that's done, one, because in the application from the permit point of view, but also because we want to learn what's exactly happening in our subsurface. Now, a lot of things what we have learned, but the major conclusion is that there is a lot of things to do still. But that is a proven and technology which can be applied and works very nicely. Now, thank you very much.
Thank you very much, Bas, for this very nice presentation on this aquifer thermal energy storage. We unfortunately don't have time for a question right now, but feel free to fill up the form. So if we have time at the end of the webinar, you can directly ask Bas, or we will make it possible to answer those questions in the Q&A sessions otherwise. But thank you again very much, Bas, for your presentation.
You're welcome.
And Lucas, if
Yep.
you hear, perfect.
Managed to join.
That's great to hear.
Do you see my screen?
Yeah, perfect.
Awesome.
Sorry.
Okay, yeah, then let's start, I guess. Yeah, my name is Lukas Seib. I'm a PhD student from Technical University of Darmstadt, and I'm here for my colleague Hung Pham. Fortunately, did not make it today. I will do a small project presentation of our seasonal crystalline borehole thermal energy storage that we constructed in 2022. Perfect. So we have a project called SCUS in Darmstadt, which is a German abbreviation for seasonal crystalline borehole thermal energy storage. Goal of this project is to construct a medium deep borehole thermal energy storage as a demonstrator on a technical scale. So we have 3 750-meter borehole heat exchangers with a spacing of approximately 8 meters. So no complete large-scale system, but just a small demonstrator to demonstrate the technology in general. Goal is to do an experimental characterization of the operation phase and then use this experimental data to validate and calibrate our numerical models, and then in turn use these to do economic and environmental analysis, and then after that also practical integration into the district heating system of the campus. The project is funded by the German Federal Ministry of Economy and Climate Protection and is also part of the European PUSH-IT project, which covers multiple thermal energy storage projects as well. So generally, what are the arguments for medium deep borehole thermal energy storage? So Romain already did a small introduction into BTES in general. So with surface BTES, our idea was that the problem can be that they are often located in upper aquifers, for example, which can be used for drinking water extraction. So there can be a negative thermal influence, or there likely will be. So our proposal was, or the proposal of my colleagues who started this whole project, was to go for medium deep boreholes where these upper sections can be thermally insulated. For example, in our case, this is done by using thermally insulating cement, and store the heat in these deeper sections, basically to reduce the thermal influence on any aquifers used potentially for drinking water, for example. This has a few upsides. On the one hand, we have less surface occupancy, and generally in these deeper sections of in specific crystalline, in our case, we have generally low permeability and therefore low conductive heat flow and low heat losses in turn. So our field looks like this. Here located in Darmstadt, in the center of Germany, more or less, and here in the southeast of Darmstadt, we have the University Campus Lichtwiese, and here is our Borehole heat exchanger field. Constructed were, it's a little bit confusing maybe, only number 2, number 3, and number 4. And then we also have 3 groundwater monitoring wells surrounding the storage, number 3, 2, and 1 again. And then we also have these orange dots and the purple dots. These are basically extension options. So if you would want an economically viable storage system, then there would be the option for the university to enlarge the system to either these 19 or 37 heat exchangers, for example. But currently we only have number 2, 3, and 4. Yeah, these wells were drilled in 2022. This is now highly specific for Germany, of course, and then also for the situation in the federal state of Hesse, because this also differs. So just a few prerequisites that we had to do is basically first the submission of a main operating plan, which is required by the German Federal Mining Act. And this basically consists of a lot of technical and safety documentation. So borehole design, geological prognosis, sealing concept if something goes wrong, and also a few different other analysis. And then we also had to register with the Hessian Agency for Nature Conservation when it comes to our heating, because in Hesse there's not really regulation for heat storage in the subsurface. So basically you always need a special permission for that. And during this, to get this special permission, we had to hand in basically environmental and hydrogeological assessments to evaluate groundwater and the subsurface thermal effect of our planned storage operation. And what you can see on the right is basically the drilling rig we used. So our company was Angers & Söhne. We had this rig with a hook load of 50 tons. So depth capacity would be 1,500 meters. And yeah, top drive, just so you get an impression. This is basically, again, so you get an impression how large this operation was, is the drilling side. So we have the drilling rig in the center, mud treatment and pumps here, the generators for electricity, material storage for the pipes and casing, and accommodation. So just to give you an idea how large the operation was. Then we used a whole portfolio of different drilling methods. This has a reason, of course. If you go for a deeper storage system, the drilling costs get, of course, higher than compared to shallow BTES systems. So as economically as possible by using drilling methods that are comparatively fast. So the idea was to go for a pneumatic hammer first, and then for a hydraulic down the hole hammer to get really high rates of penetration and get these drillings done as fast as possible. Unfortunately, our geological situation was, well, unfolded to be much more complex than previously anticipated. So originally the goal was to go into a more or less homogeneous granitic plutonic unit. However, we encountered quite large deposits of Permian basaltic units on top of these granitic rocks, which were rather unstable. So these pneumatic and hydraulic hammers did not really work. We had a lot of fluid loss always with them. So in the end, we had to unfortunately use basically standard rotary technique with a bentonite-based mud to stabilize the borehole. which then in the end led to quite some delay in the drilling. So what you can see here basically is kind of interesting. You can see the drilling time. So this is the depth and the time. So if you have large gradients, we made good progress. So what you can see is that in average, one borehole cost us around 30 days, a little bit less, and we were able to reduce this time quite a lot during the operation. But we also did quite a few scientific investigations. So we always tested the fluid hammer because it was also part of the project to get it working more or less. So we always did a round trip and tested it again. And due to these weak zones, especially in the basaltic units, we had to do quite a few cementations. And we did also quite a few rounds of geophysics to get some further information. And if you remove all the things that are not absolutely necessary, you can basically cut the time for each borehole for around 6 to 10 days, which then would be actually rather not completely competitive, but much better than it is now. This is the borehole heat exchanger layout we decided to go for. So we basically have we have a coaxial heat exchanger with, as I said, 750 meters of depth. We basically use standard API steel casing for the outer and the inner pipe. So we have an outer pipe out of steel to 750 meters, an inner pipe also to not completely 750 meters, but 745. And inside of this steel pipe, it's kind of special, is this blue pipe, and this is where do we have it? A polypropylene inliner. So this basically is to reduce the thermal short circuit between the inner pipe and the outer pipe. We also have this plastic pipe in there. And we also use two different types of cement, especially in terms of thermal conductivity. So we have in the upper section here, as I already said in one of the earlier slides, a low thermal conductivity cement, in this case 0.6 watt per meter Kelvin, and in the low section to get a good connection between the borehole and the subsurface, we have a high thermal conductivity cement, which has, at least in the lab, a value of 3 watt per meter Kelvin. Then there's the issue of well path deviation. Of course, in the optimum case, all boreholes are completely vertical. However, our boreholes, most likely due to the geological features, deviated quite a lot towards the northeast. So in the end, the distance of 8 meters in the end ended up to be around 40 at the bottom. So this of course has implications for the effectiveness as a storage system. So if we want to use our 3 borehole system, for example, this has a reduction of storage efficiency or storage utilization ratio. So how much heat can we extract from the heat we stored of around 7 to 10%. And overall, the deviations are between 2.3 and 3.3%. Of course, degrees, not percent. Of course, we could have used directional drilling to get as vertical as possible. However, that would have increased the cost as well. So the idea was to go again to try a rather cheap approach first. Yeah, and then following the drillings, we did quite extensive experiments on the storage system in the past year with an artificially created heating load. As I said, for heating up the subsurface, we needed a special permission from the state authority. So the first thing we did was a geothermal response test, basically, to estimate the in situ thermal properties of the borehole heat exchanger. And then, as a second part, we did quite extensive testing of all borehole heat exchangers with more or less realistic heating and extraction cycles. So we basically heated up the storage and cooled it down in alternating cycles. So 6 weeks of heating, 4 weeks of cooling. And this was basically how these experiments looked like, a little bit confusing, but basically we have our 3 boreholes here. They are all connected to a heating unit with a heat exchanger, and we basically pump the fluid through the boreholes through the heat exchanger, heated up into buffer storage, and then back into the borehole. All of these experiments were monitored with temperature sensors on the wellhead and volume flow sensors, of course. And in the inner pipe, in the outer pipe, and in the grout of the borehole, we had fiber optic cables to also measure the temperature variability over the depth for each heat exchanger. And everything was also monitored in these groundwater monitoring wells, at least in the upper section. During the cooling cycles, basically cooled the whole thing with an air cooler. Yeah, this is the results. It's really fresh results, so I cannot really tell you a lot about. The cycles were finished just a few weeks ago. So we basically have 5 heating and 5 cooling cycles. If we zoom in one of these cycles, we have here the inlet temperature into the storage, and here the outlet temperature. And you can see here these variations is basically the daily variations of the ambient temperature. And here the last cycle, we tried something different and went for daily variations of heating and extraction to test, for example, something like a solar thermal heating of the storage system where we can only heat during the day. And yeah, these data sets will now be used for calibration of our numerical tools. Mostly we use FeeFlow and COMSOL. And the first results are also very promising already. And these results will also be published, these data sets, to be used on other modeling tools, for example. Yeah, of course, we do not only want to test the system in theory and practice, but we also want it to be connected to the district heating system. So first, it will be further used as a demonstrator for further experiments in 2 further research projects in PushIt, where we will now, this started this week, actually, the connection, where we will connect the storage system with the heat pump to the district heating network of our campus. This will, well, the experiments running there will be happening end of this year. And then afterwards, the storage system with our 3 boreholes will definitely be connected to this newly built building here, basically in an extraction use. So we only use it for heat extraction and occasional regeneration with excess heat from the building. And then there's always the option for the university to go for a storage extension, but that is not decided yet. Yeah, what are the first conclusions from this project? So basically, we were able to construct all the 3 boreholes. Originally, by the way, 4 were planned, but because of cost increases, especially related to the complications in drilling on the first hand, but also in price increases caused by, for example, the war in Ukraine, we were only able to make these 3 wells. The drilling progress was delayed quite a lot due to the complex geology. However, we were able to cut the time we needed quite a lot already during the process. And all the practical experiments were conducted successfully. What's upcoming now, we will use the fitted data of our test cycles to assess the storage properties and investigate the potential of especially larger systems, so more or less economical systems, and then conduct coupled simulation of the system with district heating systems for environmental and economic assessment, and then also, of course, investigate the impact of the test cycles on the groundwater. Yeah, thank you very much. And I'm open for questions if we have time.
All right. Thank you so much, Lucas, for this great presentation. I think we have time for one question before the break. Any of you have this one?
Okay, apparently no questions for your presentation, Lucas. But thank you very much for presenting. I actually would like to know if you could fill in a form that is that we've prepared and that is listing all the improved concepts of large thermal energy storages that are available out here. And I think that the BTES that you've shown is definitely an improved concept compared to what we've seen previously studying this. So we would really like to include this in our list of improved concepts of LTES. I'm sending a link in the chat right now, so that you can have
Yes, of
access
course.
to this. And basically, improved concepts of LTES is either one of the existing 4 that has been improved, or it can be reuse of existing infrastructure, for example, and things like this. But actually, just before we go into the break, I can see that there is one hand that is raised. So please, Kashif, ask a question.
Yeah, thank you. Thank you so much, Lucas, for a very interesting presentation. I just have a curiosity. It's not more like a question. That I know there is like a lot of environmental protection laws, and it's not allowed to inject other type of fluid inside the borehole. But in your project, you have think about it like some other heat transfer fluid other than water, or mixing it with some glycol or something like other than water, if you have tried.
Yeah, interesting point. Yeah, so we used water actually because it was required by the authorities, because it was much easier with just water to get the permission. However, by now, just recently, a few weeks ago, we changed the water to a water glycol mixture. So because the storage is not running now during the winter, or during this winter, so to be on the safe side, but also to reduce corrosion on the steel pipes. So that's why we changed it now to a water and glycol mixture, and I believe 25% glycol.
And do you find any difference in the thermal capacity, or is it because of increasing energy density of the, or?
Oh, we did not run the store. We did not run anything
Okay.
yet with the new fluid.
Okay, perfect.
So
Yeah,
I have no practical experiences yet.
Yeah, thank you.
Thank you.
Very interesting. Thank you, Lucas. And thanks everyone for this first part, for listening, and for being available to the speakers. We'll go for 10 minutes break, and we'll be back at 12 past 10.
Nice to meet you all. Thank you for attending this webinar. Now I'm going to talk about stakeholder engagement and public perception of LTES project, and I will be focused on a treasure project which is currently running. But firstly, I would like to start with a little bit introduction of who we are. I'm coming from the Phoenix. Phoenix is a company which has more than 17 years of experience of engineering and consulting services. We are expertise in sustainable technology and built environment, and we are actually supporting other partners with their communication large of new product service to make sure they are well known on the market, and we also support their go-to-market strategy and dissemination and exploitation strategy. Me personally, I am project manager at the company, and I am responsible for proposal writing, exploitation, and economic analysis of our action. Sorry? Okay. So let's go into the topic of the presentation. Why we have stakeholders and why they are important in this kind of project is because these LTES pits, they are usually large, and we need public acceptance. We need public acceptance. We need their sorry, I hear some voices. Okay, so we need to make sure that actually these solutions are accepted by large community, and for that it's necessary to engage with these stakeholders. But we don't need not only to have like technical excellence, we also need to have
have proper communication established, and we need to have the involvement of these stakeholders from the early stage of the project. And therefore, with our treasure project, we have our website developed from the beginning of the project. We also established like the branding of the project to make sure that when we start to talk about the project, it's always presented under one logo, under one image. And we are quite active on social media, where we present our recent developments, our attendance of the events where we are presenting, and so on. But we started with the stakeholder development. So for our project, we have identified, as you see on the screen, a list of our stakeholders, and we also identify what their needs and what is their main concern. So, for example, for the industrial groups, we know that they need to have some cost effectiveness of the heat storage, and they need to be like sure that our solution can be integrated into their existing solution. So they are mainly concerned about the business disruption, some ROI, uncertainty, and regulatory complexity. All these factors needs to be considered when we are communicating with them, when we are sharing the result. And for example, general public, they need to have local benefit. So we need to make sure that we create the job, we provide the energy, and we clearly identify that our solution is clear, safety, and there is actually purpose, and it's needed for their local benefits. And actually, there is quite theory which was described really, which is called NIMBY effect, which says that it's not in my background, which said that usually the general public support these kind of project, but they do not want to have this project at their background, at their local area. So we need to showcase that it's actually beneficial for them to make sure that it brings more benefits than it has possible issues. And I could go more in details, but this is just general first two examples where we are focusing with our dissemination and communication activities to our stakeholders. And we also identify for our stakeholders what is their influence level and engagement priority. So we know how they can influence our results, our solution. So we know that we should focus on industrial group. We also know that we should focus on special audience, policymakers, which is really important because in our strategy we set up that like the social acceptance, that policy makers set up the ground rules, and based on the ground rules we can apply our solution to community and the market. And we also know that community associations are very important, stakeholders from the value chain are very important, and we know how to, or we suggest how to engage with them. So for example, for industry groups, we are trying to develop a transparent communication. For special audience, we are providing the continuous update with the expert change. So we are participating at the webinars, at the workshop where we share our knowledge, our funding. And for the policymakers, as it's similar, so we are collaborating with them from the early stage of the project, and we are trying to make sure that our results align with the standards and with the law which is set up by them. And yep, so this is a general overview of the stakeholders. And for the treasure in the action, so as I already mentioned, treasure is quite active on the social media and on the website. We have website which was developed from the beginning of the project, is one of the main communication tool where you can find all information about the project, what we are going for, where we are aiming for, what is our main goal, what is our funding, who are the consortiums, so who are the partners of this project. Excuse me. You can also find any public documents and also publication, so which will be shared once we have solid results, public deliverables, and also our partners use their like promotional materials, and you can also find their newsletter, which you can also subscribe from the website. So please feel free to subscribe it to not miss any updates regarding Treasure project. And actually, Treasure project is quite active with the cooperation. So we have established cooperation with several platform with renewable heat and cooling, and we also quite involved in build-up, where we are providing some press releases, news about the development, and so on. And we are also, as I already saw, some cluster project here in this webinar. So we are quite active with other projects where we are sharing our knowledge, we share our backgrounds, we share our finding, and we also promote our result, and we use it to enrich our network and to make sure that our results are spread as much as possible. Another part of our activities is satellite initiatives, and for this we are trying to establish exchange between another project and 15 satellites. And at the end of the project, we will organize a quite large workshop where the results and finding from these initiatives will be presented, and hopefully it will be a fruitful workshop where we share our main outcome, main achievement, and we will also discuss our plan and strategy for future development of Treasure and any other energy storage projects. And as I mentioned, Treasure project is active on the social media, mainly on the LinkedIn, where we provide news articles. We also discuss partners activities, so to make sure that all partners know where the other partners go in what kind of event, to make sure that they can meet there and discuss further steps. And we also share our clustering activities. On the right side, you can see that we already have quite a number of the followers, and yeah, please feel free to check our LinkedIn profile and do not hesitate to get in touch with us. We also have already created introduction video, which is graphical video where we introduce our project. Actually, I will put it into the chat to make sure, because I don't want to play it right now because there is no time, but I will put it in the chat to make sure that you can watch it later on. Where is it? Here. Okay. Okay, it is in the chat, so feel free to watch the video when you have time. It's just 2 minutes to introduce Treasure video, but at the later stage of the project, we will also create a complex video which will include interviews with the key partners and also some filming from the demo site and interviews with the key partners of the project and with the key results. We are also planning to create some shorts video which would highlight like our test and some main results, and that's planned for the YouTube and also for LinkedIn. And we are, as already mentioned, we are creating newsletter which is released every 6 months. We have already released 2 newsletters, and they can be subscribed either on the website or on the LinkedIn profile. On the LinkedIn profile of the Treasure project. As you can see, we also have quite large number of the followers for our project, which is quite good, and I'm really happy for that. But I'm hoping to have more subscribers and more followers on the newsletter to make sure that we reach our audience. And we have already created pro materials which support our partners when they are participating at any kind of event. So we have created project presentation which provide general information and introduce the project, and it support when they are presenting about this project. And we have also created leaflet, roll-up, and poster. All these documents are available on the website, and partners are free to use it. And if there is any need for the update, they can contact us and we can discuss it, prepare it for them, and to make sure that pro material actually fit their event where they're participating, so that it sends correct key message and it present the thing as the partner needed. So it can be adjusted. So it doesn't mean that what we currently have on the website is final. It's like the initial or first version of pro material, which is adapted based on the needs of the development of the treasure project. And what are the future plans of the treasure project? So we are still planning to communicate on our website and social media. We are planning to publish results in popular and scientific magazines, and we are planning to have training activities for DHC school and DHC knowledge, where we are going to create training material and some videos from training lessons. And we are going to organize and co-organize cluster event close to the end project, and we will organize our final event or a special event for policymakers to make sure that all our target audience are reached, and that we actually establish the communication with them to showcase what we have done and to make sure that they know that we actually follow the rules which are set up by them. And then it can be beneficial for not only for general public, but also for policymakers, partners from the value chain, and so on. And partners will continue to participate at the fairs, seminars, and workshops and conferences to make sure that they will to share their results, their findings, and to share the main achievement of this project. And yes, this is the plan for the future. Hopefully, our stakeholders will be satisfied with our activities. And that's actually all from my side. Do you have any questions if there is time?
Thank you very much, Michel, for this presentation. We unfortunately don't have time for questions, but feel free to fill up the form, and we'll get back to those questions later. Thank you very much.
Thank you.
Okay, Alex, are you ready to do your presentation?
Yes. So this is about pit storages and the first steps when you plan a pit storage. And it's this is a mixture of what we have presented in webinars in the treasure projects. So I'll start with, do we need a pit storage? And then will it be economically feasible? And finally, something about how to get permission. And this is a bit of a repetition of what Bas already mentioned, but I'll take this from Peter's side. Peter's goes up to 95 degrees as a maximum because it's unpressurized. And you have to be aware that to store 1 kilowatt hour of heat, it will cost 3 to 4 euro cents if you have only 1 yearly storage cycle. So it's the economy feasibility of the pit storage is very much depending on how many storage cycles you can have. So what can be stored? You have to be sure that you have something to store, and that could be heat from solar thermal. That was actually the first pit storages we made in Denmark. But then you will have 1 to 2 cycles, and then you have to be very much aware of the price. But you could have even cheaper heat from waste incineration or industries from summer to winter. And if you have a co-generation plant, it's possible to add flexibility to the electricity market, because then the co-generation plant can produce electricity only if there are high electricity prices and heat in other periods. But also what's coming up now in Denmark is to store heat from heat pumps, because there are very good prices on regulation in the electricity market. So the larger the storage you have, the better. And if you have a pit storage, you have no limits for where you can get punished from the electricity companies for not doing what they want. And that's the same for electric boilers, can also add flexibility to the electricity market. And then, of course, we can reduce the peak load in winter, and that's very often fossil fuel. So that's actually, you could say, this, the purposes we fulfill now, but there will also come new possibilities, because at least in Denmark, there will be production of hydrogen, methane, methanol, ammonia, and all those production plants will have excess heat. And they have, at least some of the Danish plants, they have very much excess heat, so that you can supply a total municipality with excess heat from one of those plants. So that's the future market. And for geothermal heat, also bit storage is a good way to secure that you can use the cheap heat in the summer period, where there's not so much district heating needs. And in the future, there might also be so low electricity prices in the summer that it could be a good idea to store heat from heat pumps provided in the summer period. And if you have district cooling, you can use it as a cold storage. And the last thing is you could even use it for a Carnot battery by heating up from the 90-95 degrees to higher temperatures, and then use an organic Rankine cycle to produce electricity in periods where you have high prices. So if you have some of those needs or possibilities, then it's possible. It might be possible to have a feasibility, economical feasibility for pit storage. So the next step is then to calculate. We use software Energy Pro, and it has been developed in, I think, 20 years. And it's the most used digital twin software in the world. So it can model also if you have, for example, electricity market prices, very sophisticated market prices. It can go into Energy Pro, and it's user friendly, and it's also accepted. The results are accepted by the World Bank and other international organizations. So it's powerful, it's easy to learn, it's user friendly, but you cannot see the temperatures. So you have to specify the temperatures before you start your simulation. And energy content is megawatt hours, not temperatures in the storage. So if you want temperatures, then we use Transys. But for the first steps where we want to investigate feasibility, we use Energy Pro. One example is, this is taken from a German city. We have on the left hand the total energy system in the city, so that's, you could say, the present situation. And then there's a possibility to implement pit storage and heat pumps combined with the pit storage, and then we can calculate the new situation with the pit storage. And this example, that's with waste incineration. You can see the curve in the top, that's the present situation. And in the bottom, the yellow, that's where the pit storage come in. And you can see when the waste incineration plant has stopped because of reparations, the pit storage will supply with the full capacity needed. And also there are some peak saving in the winter period. And here's another result from the calculations. The upper curve is the same as you saw before. And then there's one where with charging and discharging, where the blue is discharging and charging is the violet. And low on the waste incineration plant, you can see in the bottom that it runs nearly 100%. Only there's still, you could see, there's still some capacity in the summer period. So if we extend the storage size, then we could even store more. About the permissions, I have taken the Danish rules. So here in Denmark, it's the municipality who has the authority to approve such a project with the PTES. And according to the Heat Supply Act in Denmark, there has to be a positive economy to the consumer and to the Danish society, and also emissions have to be reduced. To calculate that, there's a manual issued by the Danish Energy Agency, and you have all the prices for electricity and the heat sources in this manual. And for the investment, we use, if we don't have better prices, we use prices from the Danish Energy Agency's technology catalog. So the plant owner must elaborate such a project proposal, and it has to be approved by the municipality. And that's one step. Another step is the law of planning. Law of planning, I think it's similar in Europe, but law of planning regulates the area utilization. So every municipality makes a municipal plan every 4 years, and there's a public phase of 8 weeks as part of the process. And they can add theme plans. But if PTES comes up, they have to look if it's okay according to the municipal plan, and then there has to be made a local plan where this project is visualized. As part of this local plan, there has to be a screening of environmental consequences. And this screening can mean that you can go on with the project, with the local plan, or you have to make an environmental impact assessment report. And if you have to make an environmental impact assessment report, then the background is, of course, all the plans already made and all the things decided in the municipalities. And then you have to compare the present situation with the situation where a PTES is included. And that's the situation for the landscape, differences in the landscape, differences in biodiversity, climate conditions, consequences, and conditions for groundwater and surface water and wastewater, and human health, and also cultural heritage, risk of accidents, and traffic. So all those has to be taken into account in the environmental impact assessment if you need to to make it. I have two cases. First one is from Dronninglund. It was implemented in 2013 to 14. And as you can see in the foreground, there's a huge solar thermal area, 37,500 square meters. And then in the background, you can see 6,000 cubic meter pit storage. And combination with the pit storage was in the beginning an absorption heat pump to cool the storage in the winter period so that the storage capacity was extended. And it was connected also to bio-oil boilers and gas engines in the beginning. For the permission procedure, the municipality said first that there was no need for an environmental impact assessment report, but some of the neighbors, and that was actually not complained because of the storage, it was because of the solar thermal part. They didn't want to look at the solar thermal part, so they complained, and there was, you could say, a small mistake in the screening, because we had not taken into account that we might use groundwater for filling the storage, and this was not described. So we had to make an environmental impact assessment report. So besides the local plan. And if we go to the environmental impact assessment report in Dronninglund, I have taken the most vulnerable parts out. You can see on the right side, the red dots, that's the area. And you can see we are in a forest. All the green is forest. So we are in an area where if we go two back, then you can see the forest, and you can also see the storage in the middle of the forest. And we have a rule that there were no buildings 300 meters from the forest is allowed, but the municipality can say, okay. And they said in this case, if you have trees on the banks of the storage, and you will hide the buildings, then it will be okay. So that was accepted. So here you can see the landscape visualization, and if trees are coming up, you cannot see the storage and the buildings. And that's the situation today. It's not seen. There was another vulnerable part, and that was cultural heritage. Our old Vikings, they had an idea to make the funerals with a hill, and those memories, you're not allowed to have buildings within 100 meters from them. And as far as you can see the circles, that we have problems that these 100 meters will go into our area. But the buildings was placed so that it was between the circles, and also there was no changes in sight from the memories and to the memories. This was an old gravel pit, and actually it was not very nice when we started, and so I think the landscape was nicer when we entered the project. The third vulnerable part is groundwater, because we are not allowed to heat up the groundwater to more than 20 degrees. So we had to make calculations. What would the groundwater temperature be? So this is the distance from the storage, and you can see if we go 27 meters away from the storage, then the temperature after 5 years will be less than 20 degrees. So our estimation was this will not be a problem, but we made a drilling where it's possible to monitor the temperature if the municipality wants. The second case is Høje Taastrup, 70,000 cubic meters, not square meters as written here, bit storage, and it's heated up to 90 degrees constantly, and therefore we had to change material to PP liner. And there was a screening of the environmental impacts made by the municipality, and they said, do you have Natura 2000 areas? No. Do you have protected fauna, historical and cultural landscapes, and so on? They went all those through all those questions and said, well, the project can be implemented without an environmental impact assessment report, because we are in the countryside where actually this will not hurt the landscape, and there's no groundwater problems because it's not a drinking water area, and traffic is does not. Of course, in this you also, when you screen this, you also have to take into account what happens in the implementation period. But here, the traffic would not harm, would not cause problems even in the implementation period. So that was all from my side. I don't know if time for questions.
All right. Thank you very much, Alex, for this nice presentation. We actually have time for some questions, so feel free to just either ask in the chat or directly to Alex. So Kashif is asking you, Alex, what is the energy storage material inside the PTES? Is it only water or some other type of storage medium?
If Alex is not connected anymore, I can answer for him. So the water, the storage medium inside a PTES is typically water, and it doesn't have a mixture with other chemicals. Given the volume that is required, that would be a lot of chemicals required. But it is treated such that the pH is rather high. So this is as to protect against corrosion. The pH is about 9.7. And it is all the salts and the oxygen are removed from the storage, such that again it also protects against corrosion. Basically, the water quality required inside a pit thermal energy storage, but also a tank thermal energy storage, is the same as what is used in district heating in Denmark. So there are clear guidelines as to the amount of salt that can be contained in the water, and the pH that should be put in. So it's water and treated in a specific way. Yeah.
Thank you, Geoffrey. So I was curious, like if you tried with some like sensibility storage medium like sand or some other type of like rocks or something like this filled with that.
That's a very relevant question, and actually there have been some concepts that have been tested at pilot scale, so rather small pit thermology storages that used a mixture of water and gravel. Sorry, water and sand. So the pit was both. It was sand and water inside the storage, but none of the, let's say, commercial projects that we have seen, so at large scale, have been implemented with this concept. But it is something that is studied, and I think one of the other EU projects, besides from Treasure, is looking at a similar concept where it's a mixture. It's a mixture of sand and water.
Thank you.
In the meantime, I can see that Alex also answered in the chat. Yeah, it's saying that the water is treated with reverse osmosis in a PTES. Yes.
Maybe I can take a question that I've got on the form for Bas, if he's still part of the meeting. Yes, I think he is. How flexible is ATS operation in terms of, for example, daily balancing compared to TTES or PTES? If you can ask this question.
Depends a little bit on what you exactly want, but the major philosophy of ATES is seasonal storage. But what you can do on a daily basis, so that means that you store a large quantity of heat to reuse it in another season. But by using the pumps, you are more flexible. So per day or per hour, you can provide heat to the network or whatever. But it's not that you use it. The major design is not for the short term. So then it's better to combine it with a TTES, a smaller TTES for the daily flexibility, because you want to prevent that the pumps will switch on and off very frequently. So it's better that I have a stable operation. But it's not impossible, but that's more the general way how it will be used.
Thank you.
I think in general, it's I think for each solution you have to think, okay, what's exactly the demand? What's the energy requirement? What's the amount of heat which is available? What type of users do you have? How do they want to use the heat? And then I think, yeah, that you should look what is the subsurface, what's the environmental, how does the area look like? What kind of connections are there? What kind of other heat sources or storage capacities are available? And then you have to look for an integrated solution. And I think, then some technology are more developed for the large scale. So you can create big buffers like the PTES. I understood is better that you have more cycles because that's for the economic better. TTES, I think it's more to have more flexibility on a very quick short term. So I think, sometimes also the combination of the technologies which really help. And to be honest, that's also the fact in the Middenmeer case, where you have the large scale data system, but the farmer itself is having a very is a 6,000 cubes TTES system, which is also on its own plot, where we have the daily and 3 days heat buffer, which also makes it more flexible for him to choose what kind of technology he will use for the heating or for the charge of heat into one of the solutions.
All right. Thanks a lot, Bess. I've got another question. So just curious to hear if CTES have been considered as part of Task 45. And CTES has a great potential in terms of volume and energy and power, which we see now with operating system in Finland and Sweden. But perhaps it is too specific to countries with crystalline bedrocks as in the Nordics. Who could answer this?
You mean caves or not?
I think so, yeah.
Yes.
Or cavern, yeah.
Yeah, of cavern. Yeah. I see some development in Finland, but also in sort of Scotland, where they also and sometimes you have the alternative for mine storage, so that they use old mines to create and heat buffer. So I think it's what you already mentioned, quite you need unique conditions where you have a cavern or you have a mine or something which can be exploited, but then especially it's interesting to see how the water can be stored, can it be kept on the same place or not. So I think it depends from site to site and also maybe from country to country if it is a realistic option or not.
Thanks a lot. A question that I've got is in terms of seasonal variability and cost-effective, competitive, and perspective, what kind of technologies can be most promising used in the future? Who would like to answer that?
I can take this one if no one else wants to chip in. As we've seen, some technologies are per design more prone to be used for seasonal storage. We've seen that BTES, but also ATES specifically, is very well suited for seasonal variability. It can be used both for heating and cooling because you have a hot well and a cold well, so you can really use it for both, and that's an interesting feature. But as Romain had shown in his introduction, the volume that you will have in terms of available storage are quite big for these applications. So you also need an application that requires a lot of excess heat and a lot of demand in the winter. So these two would be, let's say, the most suited by design for seasonal storage. But we've also seen that pit thermal energy storage is also quite appropriate for seasonal storage, as it's been used in solid district heating, especially in Denmark, so far for the storage of excess heat in the summer and reuse in winter. And then the PTES also has the advantage of being able to be used as a buffer storage. So I'm not sure exactly how the question was framed, but I would say that for purely seasonal storage, probably it's a good idea to try to see if you could use a BTES and an ATES, or an ATES if you have enough heat demand, and if let's say the heating profile that you need is rather stable. Otherwise, for seasonal storage with more variations in the demand, you could go for a PTES, or you could, as Bas suggested, combine an ATES with a buffer storage, or a BTES also with a buffer storage, in order to do the more daily variation. And then at the end of the day, it's all about looking at the geotechnical and the geological conditions of your location. If there are no aquifers available in the area, then probably you shouldn't do an ATES. If you have groundwater in the upper layers of the soil, then probably at least a shallow BTES will not be accessible. Then you would have to go for a deep BTES. solution, as we've seen in the second presentation today. So it really depends a lot on the local conditions, and also you have to make a let's say a rough techno-economic estimation of your case to see what would be most suited.
All right, thanks a lot, Geoffrey, for this answer. Johanna, are you ready, or would you prefer that we just move on to the break and come back in 10 minutes with your presentation?
Okay, yeah, probably we will move to the break, but there is actually one last question in the chat before we move on to the break, asked by Puneet. Are PTES designed for northern climates, for example, where there's snow and where it can have significant impact on the lid? What design aspect needs to be modified compared to benchmark design in Denmark and in Germany? Puneet, would you like to further elaborate on your question live, or should I just answer it right away?
Yes, I can just add a little, Geoffrey. I mean, yeah, we worked on the project together, and I think it's important. It would be interesting to see like the snow modeling on PTES, and if there is any practical experience and what it adds to in terms of cost on lid, for example. So that aspect is, I think, quite missing. So I'm not sure if any of the research institute at least is working on this aspect. So that would be nice to know.
Okay. Yeah, I see what you mean, and it's indeed an interesting question. So far, there have indeed not been any developments regarding to taking into account potential snow loads during the winter. Currently, the designs have been made in places where the snowfall is quite limited, so this hasn't been an issue. But there are several possibilities that can be considered to solve this issue. The first one is to make a cover that has improved mechanical resistance as being studied for urban areas. So there are some concepts that are being looked at in Austria, for example, to see how you could integrate a pit thermal energy storage in an urban environment where you could reuse the surface as a parking lot, for example, or as like for cars to be able to come by, these kind of applications. And for that, some specific designs are being tested with floating elements, with different, let's say, different options are being studied, but nothing has been developed. That would be one first solution that could be possible. And then another solution, depending on the amount of snowfall, could be considering putting some, let's say, heating or melting elements on top of the storage. I know that there are some IEA energy storage projects that are focusing on de-icing of roads using thermal energy storage, and this kind of solution could potentially be integrated into the lid of a PTES in these kind of areas. So these de-icing solutions are basically heat exchangers that are put at the very surface of a road, for example, and they use a thermal energy storage to melt the snow as it comes, and then have available heat when melting of the snow is needed, melting of the snow or de-icing in general. So that would be my current status about what could fit this specific need.
Mm-hmm. Yes.
If you need any reference compared to these two projects that I'm mentioning, please reach out. Treasure is looking into I think one of the demonstrators is looking into these advanced covers for urban areas. But there has been this project in Austria called GigaTES that has been looking at these kind of pit thermal energy storage before. And then the other task is task 38, I think, from the energy storage TCP. If you need the reference, I can put them in the chat if you want.
Yes, that would be nice.
Okay.
Thanks a
I will
lot,
do that.
Jeffrey.
I will do that during the break then. And but thank you for your question.
Thank you.
Yes, thank you very much. So I guess we can go on a break and come back at 11:25. Yes. See you. All right. It's 25 past, so I guess,
Yeah.
Johanna, you can
Yes.
start.
Okay. I'm sorry for the delay.
No worries.
The worm is in. So now, good morning, everyone. We are going to explore a crucial topic for Europe's energy future. What do common EU rules decide upon procedures covering European member countries regarding LTES projects? Recognizing the urgency of climate action and energy security, the European Union adopted the revised Renewable Energy Directive, known as RED III, on October 18th, 2023. This directive is a cornerstone of the European Green Deal, aiming for ambitious targets, climate neutrality by 2050, and an intermediate target of at least a 55% net greenhouse gas emission reduction by 2030, with renewables making up at least 42.5% of the Union's gross final energy consumption by 2030. A key objective of RED III, and this is particularly in the Articles 15 to 16F, is to significantly simplify and accelerate the permit granting procedures for renewable energy projects. And critically for us today, this explicitly includes associated infrastructure like thermal energy storage facilities. The directive acknowledges that lengthy and complex administrative procedures have been major barriers to investment and deployment. So RED III aims to remove these bottlenecks, making it easier and faster to get renewable energy projects, including LTES, off the ground. The focus will be on renewables acceleration areas, which is the core idea of the RED III, in my opinion. But let's first have an overview. RED III introduces several significant changes to streamline the permit granting process, including LTES. These articles you see here focus on creating a more predictable and efficient environment for developers. So first, it all starts with Article 15b, where the member states are required to map out areas suitable for renewable energy, including storage. And then we come to 15c, which is the game changer I told you already, because this is designating specific zones for accelerated development. Further on, it emphasizes transparent and effective public participation and establishes clear organizational principles and maximum deadlines for permit procedures. Specifically, it has faster deadlines for projects within the renewable energy acceleration areas. A crucial presumption that gives legal weight to renewable projects is the overriding public interest. What does this have for what legal is? I'm sorry. What does this indicate? In cases where renewable energy projects conflict with other legal interests, for example, certain environmental protection aspects under specific EU directives like habitats, birds, or water frameworks, will not be overweighted anymore, but be not as important as before. So, but now let's dive in the concept of renewables acceleration areas. The concept of acceleration areas covers both the territorial area level, which you see above, and the approval level. First of all, in accordance with Article 15b, the member states shall carry out an assessment of the domestic potential and available land required for the construction of renewable energy plants, including LTES, to achieve the European expansion's targets for the share of energy from renewable sources. By the 21st of May this year, so yeah, actually it should have been done by now. How does that work? The renewable energy areas are to be identified in particular on the basis of energy factors such as availability, generation potential, and the grid situation. Then, within these renewable energy areas, as a subgroup, there are designated the so-called acceleration areas, which will be by February 21st next year. This designation of acceleration areas is in turn based on environmental factors. It must be examined whether the use of a certain type or certain types of renewable energy is unlikely to have a significant environmental impact in view of the special features of the selected area. When designating acceleration areas, a strategic environmental assessment and, if necessary, an FFH impact assessment must also be carried out. So this is something new because normally these environmental assessments are later in the process. Actually, it's in the permit granting procedure, but what the RED 3 does is to change this. So the most work is done on the area level by the states, and if it is planned as renewables acceleration areas, then it's very it's much faster later when it comes to the project itself, because the states already have done most of the environmental assessment. Well, how big are the environment, the acceleration areas? It is not so clear because they should, all in all, taken together, have a significant size. Well, it's not clear what significant means, but it must contribute to achieving the objectives set out in the directive, which I showed before. So next one, if you have that renewable acceleration areas for 1 or 2 energy source, on the approval level, it's certain. There are certain simplifications due to the elimination of, or at least the modification of certain complex review obligations under European environmental law. If the rules set out in the plan are complied with and suitable mitigation measures are implemented, the impact assessment are no longer required on the level of the project permit granting procedure. Instead, there is only a screening taking place. So the concrete project must be examined to determine whether, in view of the ecological sensitivity of the geographical area in which it is located, it is highly likely to have significant unforeseen adverse. So unforeseen meaning not already been examined on the level of area designating. That were not identified in this strategic environmental assessment. And if applicable, the Habitats Directive impact assessment at planning level, and that cannot be mitigated by measures provided for the plan or proposed by the project sponsor. If no highly probably significant unforeseen adverse effects are identified in this screening within the deadline set for this purpose, which is 3 months, the application is deemed to be approved from an environmental point of view. So that is all. You have to do the screening and then it's okay. You can do it. If on the other hand, the screening identifies highly likely significant unforeseen adverse effect, the project must in principle be subject to a subsequent assessment, which may subsequently lead to a refusal of approval. So what can we take with us from this very complex concept? Yeah, well, at the approval level, the review of certain parts of European environmental law is no longer required and is replaced by a screening with a subsequent review of, if necessary. Instead of a review, wind energy and photovoltaic projects can be directly subject to mitigation and compensation measures. At planning level, the designation of an area as an acceleration area requires a corresponding qualification act with its own. So what is important to know for storages in this acceleration areas is that it's only, it can only benefit from that if it is a so-called co-located energy storage, which means it's including combining different renewable energy sources with a facility producing renewable energy and connected to the same grid. However, in Germany, this definition is even more narrow, so we come to this later. Well, the organization and main principles of the permit granting procedure set a comprehensive scope, so that it is covering all administrative permits for construction, repowering, and operation of renewable energy plants. Crucially, this explicitly includes co-located energy storage, as I said, and the necessary grid connections. There's also formal and accelerated deadlines. I'm sorry. There are 3 sets ambitious maximum deadlines with a significant differentiation for projects in renewable energy acceleration areas. So in these areas, we have to, or the authorities must confirm that the application is complete within 30 days, and otherwise in 45 days. And the maximum duration of permit procedure for co-located LTES is in the renewable acceleration areas 6 months, and outside the renewable acceleration areas 12 months. Member states shall also provide contact points and information to guide and facilitate the applicant during the entire administrative permit application and permit granting procedure. It should include the steps relating to the protection of the environment in a transparent manner, provide the applicant with all necessary information, and where appropriate, involve other administrative authorities. Which is also very, very helpful is that the member states have to make available a manual for developers of renewable energy plans and provide that information online. This is in Germany, it's really crucial because German law is very complex when it comes to renewable energy plants, and even more complex when it comes to storage, because actually it doesn't exist explicitly by now. So you have to ask yourself why, how to, yeah, how to get it permitted. And this will be much easier in the future. Yeah, of course, member states shall also ensure that the deadlines for the permit granting procedures set out in the directive are met. The main idea is that the applicant shall not be required to contact more than one contact point during the entire procedure. For example, in Germany, you have to get to various contact points before you get one project done by now, so this will be much easier in the future. Yeah, there's some.
Johanna, just for your information, we're running a bit out of time, so if you could try to wrap up.
Okay,
soon, it would be great.
What
Thank
is
you.
the specific implications for LTES by RED 3? Maybe to sum it up, they are explicitly included. This is the first time that they include thermal storage in European law, and this means all kinds of LTES we talked about today are included and are direct beneficiaries of the accelerated permit granting procedures if they are possibly defined as co-located energy storage, which is normally given. It's faster deployment and reduced administrative burden, higher legal certainty and grid integration and flexibility, and the benefits in the acceleration areas are, as we've seen before, even higher because it goes much faster and environmental assessments are not necessary anymore. Just a quick example of how Germany implemented this, because while the RED 3 sets the overachieving framework, its effectiveness depends on how member states transpose it into national law. For example, the definition of co-located storages, which is crucial because only if a project is possibly defined like this, it can benefit from the benefits. So the definition, but however, German definition of co-located energy storage in the draft of implementing it in German law is much narrower and has much higher I'm sorry, standards. So not all LTES projects will benefit from those. This highlights that while the the EU provides a robust framework, national implementation details can significantly influence the practical benefits for specific technologies. And so it will be exciting how the certain countries will implement it in their law, and and how but you can say that LTES will definitely benefit from the RED 3 in one way or the other. Thank you.
Thank you very much, Johanna, for your presentation. I see there is one or two questions even, but I guess to kind of finish on time, we'll move on to the next question, and answer those questions in the next Q&A session.
Yes. But very good questions, and we'll reconvene in September for a Q&A session, and probably we can invite Johanna to answer those questions.
Yeah.
But we'll see. Maybe we have time anyway, but we do have 1.5 more presentations to go through, so we'll see. So according to the schedule, I was supposed to present very shortly the financing aspects of large thermal energy storage, and just to take again the figure that I'll deep dive directly into my presentation. Just to take again this curve that Romain has presented, it showed the economies of scale that you have for the different LTES technologies, at least for TTES, BTES, and PTES. But what we cannot see is the total cost. So what I tried to extract is an old curve that has been done for PTES specifically. So here you see the specific investment cost on the right-hand side, but the total project cost you can see on the left-hand side with these curves and with these dots. And basically these projects are the references that have been doing solar district heating in Denmark between 2012 and 2017. So these prices are roughly from 2017, and this curve in red is the estimates from that time. If I put on the same curve the latest PTES that has been implemented in Denmark, Høje-Taastrup, we can see that it's significantly higher price. There are several explanations to this, but then based on a similar curve trend, we can see that the investment cost would be in that range at a minimum, and that means the main message I want to give with this curve is that means that when you invest in a PTES, but in an LTES it's going to be a similar range, you're probably looking at investment between 1-2 million euros up to 20 million euros or even more. So how do you finance such a project? First of all, financing in these kind of projects is needed in all phase of the development of the LTES. The first phase is the opportunity, where you assess the potential of your storage, and there you have researchers and engineers or consultants that can help you. You also have the policies in place and the local rules that need to be consulted, as we've seen with several examples today. Then you have the design phase, where more or less the experts are designing the plants and making detailed feasibility studies to define the size and specifications for the storage. This phase also requires some financing. Then you've got the tender phase, where you need to prepare the technical specifications of your LTES and prepare for the contract. And then finally, the implementation phase. And basically, it's the project owner that oversees the financing of all of these phases. So that's what we need to finance. So if I give you the same example as what Per-Alex was showing earlier, the second one that he was showing in Høje-Taastrup, this is just let's say a summary of the main technical aspects of this district heating network coupled PTES. But if I look more into the specifics of the economics of this storage, then you can see that more than half of the investment cost is the storage itself, the water filling and the commissioning of the storage. Then you have these parts that are more consultancy, tendering, design, project planning, execution, follow-up on the construction, and so on. And then this part is the specific cost for that project, where there was the need to build a pipeline that had to cross over a highway, and also a heat exchanger building for the transmission network. So that's just to show you a distribution of those costs, and these costs are distributed along the different phases that I've shown. So what you need to know is that the way to finance a large thermal energy storage in general, it depends on the kind of organizational structure you have. You can have traditional ownership by the district heating network operator. You can have co-ownership like in Hartsostrup, or you can choose a heat purchase agreement or a private actor, such as what New Heat is doing, for example. And I have a few slides on that. But there are other potential business models that could be considered, some kind of crowdfunding where the local people directly can invest in the project. You could also imagine some investment funds putting some money into such a project, but that usually requires some short return on investment times. And then leasing could potentially be an idea. So that's just an idea for discussion. If we take an example from Treasure, so Treasure has been presented earlier by Michel, but there are 7 demonstrators in Treasure, and then 3 of them have a potential private owner. So as I said, New Heat was one of them, SEC is another one, and the Solid was a third one for these demonstrators. And each time the district heating network had a different owner, except in the case of SEC, where it's the private company both owns the storage and the district heating network. In the public area, you can see that there are 4 demonstrators of Treasure where the public owner is also the district heating network operator. So that's just to give you an illustration of what I was saying earlier. Now, if we get back to Hartsostrup, which is a bit of a specific case, it's, as we've seen on the curve, it's a more expensive PTES than what we had previously known, but this can be justified because it generates more benefits to its users. So the total investment costs of the PTES were 12.15 million euros, including everything, connection to transmission network and so on, and consultancy. But the annual benefits of operations were estimated to 1.04 million euros. So that's a simple payback time of about 12 years. And the way it's distributed, these benefits, is that there are CHP plants in the Copenhagen area that can play on the electricity market and sell electricity when the prices are high. And thanks to the uses of the storage, they can make more benefits. And that's about 35% of the benefits. There are waste to energy plants that also benefit from having the storage. That's a bit less of the benefits. And then you also reduce the need for peak demand in the local distribution network, and that's actually where most of the benefits are located. And the way it has been done in Hartsostrup, it's co-owned both by the distribution company and which is Hartsostrup, and the transmission company, which is VEX. And together they own half the storage. But what is interesting is that the loan for the investment of the PTES has been guaranteed by the municipality of Hartsostrup through a credit scheme called Kommunekredit, which is a special Danish mechanism where a municipality can guarantee 100% of the loan, and that gives access to a very cheap loan to district heating network operators. Just a general overview to say that investment can be funded by equity, it can be funded by debt and or subsidies. In the case of Hartsostrup, as I said, it's a public loan that has financed, but the loan itself is being paid back by the people that benefit, or the users that benefit from having the storage. But again, there are different options such as equity or subsidies. And these financing methods depend a lot on the countries where the LTES is being developed. There are different subsidy schemes depending on where you're located. It can be a subsidy of the investment, but it could also be a tax credit. That's more the way the Danish system is organized. There are different available loans, as I've just mentioned. In Denmark, some loans are more affordable in a specific condition. And then there's this EU framework that gives access to specific subsidies. So that has just been presented, but now these subsidies available at the EU's can be facilitated, but they are also available at national and regional level. So in the EU, there are several programs available. The national subsidies are available in Austria, Germany, France, and Poland, for instance. And then some regions, specific regions, offer subsidy programs. And this is summed up in this table over here. So you'll get the slides afterwards. I will not dive into the details. So that's it for that part of the presentation. We're definitely running out of time. Sorry for that. But the last point on the agenda was a small wrap up and potentially an open discussion. For those that still have time, I think we can take 5 minutes extra for let's say follow up questions and then a bit of discussion if you're still up for it. But in terms of wrap up for this session, I would say that it was quite interesting to see from ATES, BTES, and PTES, for example, there are some common issues that are being encountered. For example, in terms of environmental requirements, we've seen several examples showing that because of the potential environmental impact of the storage, there was a need for monitoring to make sure that the authorities could see that the impact on the ground or the groundwater was limited. So that's something that we've seen in common with several of those projects. Another thing that we've also seen in different technologies is the increased costs. As you've seen on my presentation, the PTES cost can increase, and that's a very important part of the investment, which means that when you plan for a PTES, you should make sure that the envelope for your budget that is being prepared is sufficient and also contains a margin of error to account for potential increase. That's also something that I would take out from the different presentations we've had today. And what I think is interesting is that if we did this webinar 5 years ago, then we would see that there is absolutely no framework for large thermal energy storages whatsoever in any country of the EU. And now there is an EU regulative that specifically stipulates large thermal energy storages. There are several countries that have specific mention of large thermal energy storages. I'm thinking about the one in Austria specifically, but in France as well. And that's something that is showing that large thermal energy storages and their crucial role is being more and more acknowledged among the countries and the regions that need to go into the energy transition, and that's a very positive sign. So after this wrap up, I'd like to open the floor for any further comments or questions. Please go ahead if you have any right now, and then to close, I will show you the next steps of this webinar series. So for people that have not been able to stay the whole presentation, you will be able to see the replay online. Bas, maybe you have a follow-up comment.
Yeah, what I have seen, thank you very much, Geoffrey. What I have seen and also got some feedback from our high temperature ATES user is that he is very happy with the system due to an increased flexibility. And that was not something how we have designed the system, but he gave some comment and said, okay, now I'm more flexible to, if I have some surplus of heat, I can just store it. And the other angle, which we did not took into consideration during the design process, but which is now coming up and becoming more and more interesting, is also the connection with the electricity network, because net congestion problems are becoming bigger and bigger. So large thermal energy storage system can play an important role to buffer the surplus of electricity or a lack of electricity by using CHP or other ways how you convert electricity. And I think that's interesting because in general in Europe there's a lot of attention for the electricity market, and a lot of money will be invested in all kinds of technologies. But it's still about 20% of our energy need, while heat is more than about 50%. But the investments are still limited. And I think it will be interesting to see how we can make the connection with electricity and also open maybe more doors for funding and making more projects with heat.
Thank you. I think this is the perfect words to close the seminar, this first webinar. Again, a small heads up for everyone that is working with improved concepts of large thermal energy storages. Please fill in this form. We've already received a few references, especially for ATES. So from some of your former colleagues, Bas. So thank you for that. But please do fill in this form if you are aware of an improved concept. It can be a new kind of tank thermal energy storage or a new cavern thermal energy storage, anything, a new borehole thermal energy storage as we've seen today. And I can see in the chat, are phase change materials used in any of these large thermal energy storage units? The answer is no. So far, it's only been either the soil, an aquifer, so water underground, or pure water. But phase change materials are usually used for rather compact applications. And for these very large scale applications, you're looking for a heat transfer medium or storage medium that is rather cheap. So that's one of the let's say the reasons why we don't have these PCM in large applications. If you want to find large scale applications that use phase change materials, or at least some kind of phase change, you would have to look at molten salts applications, and that's going in the much higher temperature range, which is not the focus of what we consider large thermal energy storages. And before I go to your question, Thomas, I just want to say that this was the first webinar of 4. This has already been announced by Romain. But we will organize also in parallel of these webinars some Q&A sessions. The first one will take place in September, so you'll receive an email about this in due time. And you can fill the form to put in your questions. So please feel free to ask any question, and then we'll reconvene and bring the appropriate experts to answer to your questions. And then the second webinar will take place in December this year, and we'll focus more on the technical aspects of large thermal energy storages, as well as some economic aspects. So this is it. We'll send out an email to get an evaluation of this webinar. I hope we will not get too bad ratings because we went over time. But let's see. And to close off, maybe Thomas, you can ask a very quick question.
I don't have a question, but only a remark, because I think what Johanna presented is really important. We now have the chance to implement our requirements into the RED 3 and the national transition. So I don't know if it's possible, but do you think we could have the chance to collect our requirements for seasonal storages or PIT applications to give it to, for example, eject to national institutions, so that they can implement them or collect them, so that they will be considered into the national transition of the RED 3. I think it's very important, because now the door is open, and I see it only from my own geothermal project that it's very difficult to define what is necessary for the transition into national law, and I think it's also more difficult for seasonal storages. But as I said, the door is open now. We have now the chance to tell what our requirements are, and give ideas to the national institutions. So my idea would be that from this platform we could do it.
Thomas, I think it's a very interesting remark, and it's extremely relevant for this task 45, because we have been trying to target policymakers as one of the main actors that we're trying to let's say to inform and give good inputs with regards to upcoming policies. So it is part of the work that we're doing. But what I would really like for you to do is go into this form, the one for where you can put in some questions and put it in, such that we can gather it in task 45 and then see what we can do to influence at national level the different implementations that have been done, because indeed it can have a pretty big impact on how this will actually be used in practice, and who better than our group of experts to get this influence going. I hope it doesn't come to I hope it's not too how to say it's not too broad statement to say that I think the previous task 39, has already had quite a large influence on these policies. I think the EU directives, the fact that they take into account large thermal energy storages, is thanks to the work that we've been doing partly thanks to the work that we've been doing in task 39. But I completely agree with the fact that we should keep doing this work, and this is a great opportunity for us to have an influence on a very important regulation. Anyway, now we're 12 minutes over time. Thank you for everyone that stayed this long. As you can see, there are still 49 people online. Have an absolutely great day, and we'll see you later in September. Bye, everyone.
Bye.
Bye. Thanks,
Thank
everyone.
you.
Goodbye.
Thank
Thank
you.
you.
Bye.
Bye. Thank you.
Have a good day. Thank you very much. Bye.
Bye.